Why can't relativity and quantum mechanics be unified? Because they have 5 core contradictions. The first contradiction: relativity can be divided into 2 theories, special relativity and general relativity. In fact, as early as 1928, Dirac had already unified special relativity with quantum mechanics. It's just that general relativity has not yet been unified with quantum mechanics. So what is the difference between special relativity and general relativity? The most fundamental difference is this. In special relativity, time and space are flat, while in general relativity, time and space are curved. Since quantum mechanics has already been integrated with special relativity, the time and space of quantum mechanics are also flat. This is the first contradiction. The spacetime of quantum mechanics is flat, while the spacetime of general relativity is curved. Because curved spacetime has been confirmed by a large number of experiments. In the first round of confrontation, Einstein and general relativity win. The second contradiction, and also the biggest one: general relativity is built on Riemannian geometry. Riemannian geometry has a fundamental assumption. Spacetime must be continuous and smooth. Spacetime can be curved and can have folds, but it must transition smoothly and cannot have breaks. So spacetime is a lot like a balloon. Its surface must be continuous and smooth. In quantum mechanics, there is the uncertainty principle. It causes energy to undergo quantum fluctuations, and the smaller the scale, the more violent the fluctuations. When you reach the Planck scale of 10 to the minus 35 meters, extreme energy fluctuations appear. We all know that energy can curve spacetime. Therefore, violent energy fluctuations will lead to violent spacetime fluctuations. Riemannian geometry requires spacetime to be smooth, but the uncertainty principle causes spacetime to fluctuate violently. This ultimately leads to infinities at the Planck scale. This is like one spacetime being a balloon, and the other spacetime being a hedgehog. Force them together, and with a bang, everything explodes. This is the most important reason why quantum mechanics and relativity cannot be unified. Besides this, there are other reasons. For example, relativity is continuous. But in quantum mechanics, quantities like energy and momentum are discrete. There is also the issue that time plays different roles. In quantum mechanics and in relativity, quantum mechanics treats time as an external, fixed background, but relativity treats time as an internal, dynamic structure. To give an analogy, one is a fixed stage on which particles perform. The other is a dynamic trampoline. Particles can affect the shape of the trampoline. Therefore, the role of time is positioned differently. In quantum mechanics and in relativity. In physics, this problem is called the problem of time in quantum gravity. The third contradiction comes from Einstein's famous statement, God does not play dice. More specifically, quantum mechanics believes the world is random, while relativity believes the world is deterministic. As long as the initial conditions are given, general relativity can precisely predict the state of a system at any future moment. For example, if you fail an exam, general relativity would say that if the universe were to evolve all over again, you would still fail that exam. The initial state at the Big Bang determined that you would exist, and that you would fail this exam. But quantum mechanics believes the world is random. If the universe evolved again, Earth might not even exist, and this exam would be even less likely to exist. So is the world random or deterministic? There is a theory called Bell's inequality that can test this. Physicists have carried out a large number of Bell inequality experiments, and all of them support the idea that the world is random, rejecting Einstein's hidden variable determinism. Therefore, the world is random. If Earth went back 4.6 billion years and evolved again, it might not evolve humans at all. If you went back to infancy and lived your life again, you might not meet the person you love today. So, in the final analysis, the bonds and encounters between people come from the randomness of quantum mechanics. And these bonds are unique in the universe and will never repeat. Miss them once, and you miss them for a lifetime. The fourth contradiction: relativity does not allow faster-than-light motion. But in quantum mechanics, the collapse speed of an entangled wave function can exceed the speed of light. Although both agree that information cannot travel faster than light, their worldviews are different. Relativity is local, believing that an object can only be influenced by its immediate surroundings. Quantum mechanics is non-local, believing that the universe can be correlated over long distances. Through quantum entanglement, two particles, no matter how far apart they are, behave like a single whole, instantly synchronizing their states, while ignoring spacetime distance. Einstein called this non-locality, spooky action at a distance. Simply put, relativity believes that all interactions are limited by the speed of light, but quantum mechanics believes that, at a deeper level, the universe may be an indivisible whole. Seemingly separate individuals can share the same wave function. The fifth contradiction: quantum mechanics believes that information must be conserved. But relativity believes that information does not necessarily have to be conserved. For example, if you throw a book into a black hole, quantum mechanics believes that the information in that book still exists. Just like energy conservation, the information in the book continues to exist in other combinations of states. But relativity believes that a black hole wipes out all state information. Apart from mass, charge, and angular momentum, all other information about that book disappears. So the contradiction arises. One side believes information is conserved. The other believes information is not conserved. These two sides have argued for decades. So who won the argument? Today, most physicists believe, based on the holographic principle, that the Hawking radiation emitted by black hole evaporation retains the original information of that book. In other words, information is conserved. Therefore, quantum mechanics has the upper hand in this competition. Let's summarize the 5 contradictions between quantum mechanics and relativity. One has flat spacetime, the other has curved spacetime. One requires smooth spacetime, the other has quantum fluctuations. One is probabilistic, the other is spacetime determinism. One is local, the other is non-local. One conserves information, the other does not conserve information. Let's think one step further. What do these 5 contradictions have in common? If you observe carefully, you'll find that they all share one thing behind the scenes: spacetime. The first 3 contradictions are directly related to spacetime. The fourth contradiction involves locality, where causal influence is limited by spacetime distance, and non-local correlations that can ignore spacetime distance. So the fourth contradiction is also related to spacetime. The fifth contradiction is about information. In physics, information is usually defined by entropy, and entropy is related to time. Therefore, information and time are highly correlated. In short, all 5 contradictions are related to spacetime. There are so many contradictions between quantum mechanics and relativity, and ultimately, they exist because physics knows too little about time and space. Time is the physical quantity that physics understands the least. Since we can't find the answer in physics, let's look for it in philosophy. So next, let's introduce the 2 most important philosophical views of spacetime. In the 17th century, when modern science was just being born, 2 views of spacetime emerged. One was Newtonian spacetime, and the other was Leibnizian spacetime. Leibniz, this name sounds familiar, right? He's the Leibniz from the Newton-Leibniz formula in calculus. The 2 of them established 2 different views of spacetime. Let's start with Newtonian spacetime. Newton believed that time and space are external containers, and matter moves within these containers of spacetime. But Leibniz believed that spacetime is the internal relationship between matter. Time is the continuous change of matter, and space is the coexistence of matter. Newton believed spacetime is a stage. Electrons, quarks, and other particles are like actors performing on the stage. If all the actors disappeared, the stage would still exist. So Newton believed that even without matter, spacetime could still exist independently. But Leibniz believed that this stage does not exist. Spacetime is the relationships between the actors. For example, relationships like classmates or lovers. If all the actors disappear, then those relationships disappear as well. When relationships disappear, spacetime disappears too. Therefore, if all matter disappeared, Newton believed spacetime would still exist, while Leibniz believed spacetime would disappear along with it. In short, the core difference between these 2 views is this: Newton treated spacetime as an external background, while Leibniz treated spacetime as an internal relationship. I've read many philosophical interpretations of spacetime. The Leibnizian view of spacetime is the one I've seen with the strongest explanatory power for understanding the world. For example, why was there no time or space before the Big Bang? Leibniz tells us that spacetime is merely an attribute of matter. Before the Big Bang, there was no matter. If matter didn't exist, then time and space couldn't exist either. Another example, the universe is expanding. Is there space outside the universe? Leibniz tells us that spacetime is merely an attribute of matter. Outside the universe, there is no matter. So of course there is no space. Wherever the universe expands matter to, time and space are born there. Another example, why does time stop at the center of a black hole? Leibniz tells us that time is the continuous change of matter. A black hole crushes matter flat, and matter no longer changes. When change disappears, time naturally stops. Therefore, the Leibnizian view of spacetime can explain many ultimate questions. Finally, let's return to the theme of this video: the contradictions between quantum mechanics and relativity. Quantum mechanics is, in essence, a Newtonian view of spacetime. Quantum mechanics treats time and space as external stage backgrounds. General relativity is, in essence, a Leibnizian view of spacetime. Einstein said in 1952 Spacetime is not an independent existence, but the internal structure of fields. Therefore, Einstein's view of spacetime is consistent with Leibniz's. To summarize this episode, quantum mechanics and relativity have 5 core contradictions. These contradictions ultimately arise from 2 different views of spacetime. Quantum mechanics follows the Newtonian view of spacetime, while relativity follows the Leibnizian view of spacetime. Finally, don't forget to like the video. Like.